Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 57 today and we are discussing about adhesion of two viscoelastic spheres. This topic is being taken from these two papers and there may be few others. Okay, as we go along I will tell. In the last lecture we presented this definition of convolution, and then we also discussed that when there are contact between this on this elastic half space and over this area A, and because of this distribution, pressure distribution P, which is now a function of R and T. So remember that for an elastic case the P was a function of R, but now it is also a function of T. And so this C star P, that is the convolution, and pi R is in the denominator, pi rho is the denominator, and this quantity has to be equal to delta T, delta as a function of T minus R square by TR, and this is because of the kinematic condition that these two spheres in contact. So in the location where it is in contact, this condition is to be satisfied. So the solution of this particular equation has to be of this particular form when there is adhesion between them, and we recognize that this part is from the Hertz contact and this part, okay, where there is a singularity there, that comes at the singularity at the edge at R t is equal to A T, this is there is a singularity there. So this comes from the adhesion part. This is a Heaviside function, step function, and this means that at A T is less than, so R being less than A T, okay, this quantity is equal to 1, and R being greater than A T, this quantity is 0. So in essence that we have defined, okay, this function, okay, within the area of contact, that is all it means. So we will like to substitute this expression, okay, into this integration equation in order to obtain this quantity delta T and also get an expression of B0 and B1 and all that. So we will like to, so we have to do this integration over A area, and it will look something like this. So in essence, as I was telling you in the last lecture, that this is the center of this area of contact here, and so this is the area of contact, let us say, and this is the center. This is the point B, which is at a distance R from the center, and this point. So this area, the pressure varies, this quantity is a function of space, and so I represent it by L over here at this point. So this point is at a distance rho from this, at a distance rho from this particular point B. So this is C here, this is O here, and the area over here is given as rho d phi into d rho, and so this is L here. So the L, therefore this function has been written in terms of L here, okay. So from the center the distance of this point is basically L. So now I substitute it, so it will be equal to, therefore as I said that this rho, this distance is basically rho. So the rho varies from 0 to rho 1, and this phi varies from 0 to 2 pi, okay, and C1, so it is 1 by pi rho. So this is pi into rho here, and this over the area has to be defined. So the it is rho, it is d phi into d rho, and here this quantity, this is B0 over T into this is A T square minus L square. So this is square root, and minus this is B1 of T, and this is square root of A of T square minus L square. So we have to do this integration now, and here, okay, so now rho and rho gets cancelled, and this is pi here, and so this L square. So now we have to do this integration. So over here this L square, this L needs to be found out. So this L square has to be written in terms of this rho. So, this L square this is equal to r plus rho, this is cos phi, okay, these things we have done earlier actually, and rho sin phi whole square, okay. And so we can actually write it as, therefore, r square plus rho square plus 2 r into rho cos phi. And you can also get a solution for rho 1 by solving this equation. So, a square is equal to r square plus rho square plus 2 r rho cos phi. So, by solving this equation to obtain an expression for rho 1, okay, that you can obtain. So, we have done it. So, I am not going to go into detail of that, but we have done it earlier. So, as I just wrote, so equation will be like this, and so we can now solve, we can solve this and do this integration. So, rho 1 is a solution of this equation, as I said, and so this rho 1 will come out to be like this. This is simply quadratic equation, and now from the first part, so that means from this part, okay, so this will be equal to, as far as if I remember, this is equal to a square minus this is 2a square minus r square, 2a square minus r square, right. So, it is 2a square minus r square, and by, I think this is pi square by 4, this is pi square by 4, right. This is pi square by 4 here, and this is b0 of t of pi here. So, this integration is pi square into pi square by 4, 2a square minus r square, and over here this is b1 of t by pi, and this is actually pi square, okay. So, this is actually is equal to I, and so this comes out to be b0, okay, of t by 4 into pi into 2a square minus r square minus this is b1 of t into pi. So, this is okay, and so now we can write it like this. So, let us say I can write it as b0 of t into pi, and then 2 gets cancelled, 2 here not cancelled, a square, and minus this is b1 of t into pi, okay, minus this, I am just separating this r power, so with respect to r. So, I will write it here, this is b0 into t into pi by 4 and 4 into r square. So, this equation, okay, has to look like this expression over here, delta t minus r square by 2r. So, this is actually looks at delta 2t minus r square by 2r, and so therefore, from here I can say that 1 by 2r, that is equal to b0 of t pi by 4. Now, this is not this is independent of time. So, b0 actually remains independent with respect to constant with respect to time. So, b0 I can write it actually not with I can get rid of the time here. So, it is will be 2 by pi r b0, okay. So, 2 by pi r, and delta t will become like. So, here again you substitute here b0 is equal to 2 by pi r. So, it will be a square by 2 x square by r minus pi b1 t. So, that is this delta t. So, that is the way we get. So, therefore, we get the solution of C star. Now, we can want to find out that what is the total force that is applied. So, remember that we have got some solution of C star P. So, we have gotten that, and that comes out to be like this, and so we multiplied by 2 pi r and then obtain this. So, here we can write it. So, C star into F. So, F is the total force that is applied, okay. So, remember the pressure is varying, so F is also varying with respect to time, and this is 0 to A of t, okay, and so it will be, let us say this is 2 by pi r into a square t minus r square square root and 2 pi r. So, 2 pi r dr, okay, and minus, let us say the other second one. So, this was second one, yeah. So, this is 0 to A of t, and this is b1 of t, and this is a square t minus r square to the power minus half and 2 pi r dr. So, we have to do this integration, and for that we can write this, let us say a square t minus r square, this is equal to z square, and so that will be minus 2r dr, that is equal to 2z, okay, dz. So, we have need to substitute that. So, let us the first one, let us say it is I1. So, this is equal to 2 by pi r over here, and this is, let us say, I will not put the limits over here. So, 2 by pi, so now a square by 2 r square is z square. So, this is equal to z here, and this is 2 pi here, 2 pi goes out, and then r dr. So, instead of r dr is equal to z dz with a minus sign, minus z dz. So, this is equal to, so pi gets cancelled, so it is minus here, so it is minus 4 by r here, and this is z square. I am not sure if I am doing correctly, hopefully. So, it is z square. So, z square will be z cube, right? Z square, yeah, over here. So, it is z cube by 3, okay. So, it is going on fine. So, let us do it. So, z cube by 3 here. So, z cube by 3, and now we need to z, okay. So, this is equal to minus 4 by 3, okay, into r and z cube. So, z has to be replaced over here. So, that is square root of a square t minus r square, and this is cube. So, now this has to be, r has varies from 0 to a of t. So, now you put the substitute for r, and then you obtain whatever will be the value. Similarly, for the other part, so this part also we can do the integration like this. So, here finally, so that part also we can do. So, it will be r by this. So, here again I substitute a square by r minus r square is equal to z square. So, this will be z here and minus z here. So, z is easy. So, this comes out to be 80. So, this C star F, so that is, F is the total load that is applied. So, that, okay, can be obtained something like this, 4a cube by 3r minus 2 pi b1t and 80. Remember here that we do not know the expression of b1t yet. So, it is to be found out. So, how do we find out that? Because we can find out by examining the pressure field. Let us say at r tending to A. So, r tending to A we can find out. So, for that let us say the pressure field we have obtained it earlier. So, that pressure field over here, so that is given by this expression. So, this is 2 by pi r, 2 by pi r, and this is a t square minus r square square root, and minus this is by b1 of t. So, it is b1 of t and 1 by square root a t square minus r square. So, this is the pressure field that we have obtained. This is C star 2 pi r. So, this C star, it is not pressure field, it is C star into P r. So, I have to multiply it by 2 pi r. Now, that is fine. So, this is what it is. So, this is, remember, so I should say it is C star P r. So, that is what it is. So, here let us say that at r tending to A minus means just the limit A, and so that is equal to, therefore, will be equal to. So, here this term will be equal to 0. So, it will be minus here and it will be b1 t, and over here we will write it as square root of, this is A of t plus r into A of t minus r. So, this equal to minus of, this is b1 of t, it is A plus r and minus r. So, this is r tending to A. So, this is square root of 2a t, and this is A of t minus r, and so this is equal to, we know about, write it something like this, stress intensity factor divided by square root of 2 pi into A t minus r, okay, like that. So, it is from the distance from the crack tip basically. So, here therefore, this K I, the stress of intensity of mode 1 crack, so it is equal to minus b1 of t, and this is square root of A of t divided by pi. So, it is like that. So, we have obtained it, the the stress intensity factor, so K inverse as C inverse B1. Oh, so actually that is one thing I made a mistake here. So this was actually like that. So this P of RT was, so this was this is okay. So here therefore this P is equal to this quantity. So it was actually C inverse, C inverse, and so from there stress intensity factor. So here let me just correct it over here. So C, so this is not, so here let us say this is P of RT, okay, RT. So that is equal to C inverse star, and this is minus, so therefore it is C inverse star, and like, no, this is this, so therefore it is C inverse minus 1 star B1t by AT by square root of AT by pi. So that's the relation of this stress intensity factor over here. So therefore as I said that the C inverse, this stress into this convolutions can be written in the inverse form also. So we can do that. Now there is one point that needs to be considered here, is that P is equal to C inverse over here, but since we are considering at R at A, that is at the limit, okay. So that means that it is this part at the contact line, okay. So that R is equal to R at this point at A of T, this is actually the contact line. So therefore it is always instantaneous. So therefore this R to A, that corresponds to instantaneous response. So as a result this C can be replaced by C0 inverse, okay. So this is actually at the contact point, that's why. And so here so that is the way it can be written. So that is actually instantaneous, therefore it is C0. We can write, instead of having C we can write it as actually C0, and so therefore this equation remains valid for B1. We can write it C0 into K1 and into square root of AT by pi. So here we have this B1, now we have written in terms of this stress intensity factor, that is what we have done. So here we can write this A1, A cube, something like this. So A cube T, so that will be equal to, this is 3R by 4 into C star F, so minus, let us say, no, C star F, and let me do one thing, let me write it like this, this is minus and minus, this is 2 pi into 4, this is 3R by 4, this is 3R by 4 into C0 into Ki and square root of A of t by pi, square root of pi and not pi, and A of t is outside over here. So in essence this is equal to 0. So what we have is actually A 3 by 2 t square minus, this is 3R by 2 here, 3R by 2, and this is C0 and then K of I, and this is some function, something over here, this is A of t to the power 3 by 2, and then minus I have got 3R by 4 into C star df. So basically I have the equation, a quadratic equation in terms of A to the power 3 by 2. So I would like to find out that quadratic equation. So just let me correct it little part over. So it is 3R by, and this is pi here, and this is Ki here. So I guess pi should be square, this is 1 by square root, so it should be per square root, okay, like that. I think that should be fine. So now I can obtain this A to the power 3 by 2 as a function of time. So this can be solution we can obtain. So this will be equal to 2 here, and this is 3R by 2 C0 Ki and square root of pi here, and here, yeah. So this is means be plus, this should be plus and minus, so it is minus by plus. So b square minus 4ac. So it is square b square minus 4ac. So it is actually 3 r by 2 into C0 k I square root of pi, let us say, and then square minus 4 into, you can actually write down the whole thing, divided by 2 over here. So, we are trying to solve this as I said here, and so it comes out to be like that. So, 4 into so 3 by 4 into like this. So, that is already there, and then a to the power 3 by 2 comes out to be like that. And so, this is the solution, that of a to the power 3 by 2. So, let us say I find out the square of that. So, then I have got this relation. So, let me just try to expand it. So, it will be 3r by 4 square pi, and it will be C0 k I square plus it is 3r by 4 square root of pi, and here it is C0 k I square plus this is 3r by 4 C star f plus 2 into this is 3r by 4 square root of pi, and this is C0 into k I into this is square root of this is 3r whatever is there inside in the square root of term C0 k I, and this is square root plus this is 3r by 4 C star into f. So, here I have just find out the square term, and then I will like to take this 3r by 4 term outside, and so finally I will have this expression C0 pi square, this term C0 actually 304, oh this the whole thing is, this term is also square, I should have done that, this is square also, okay. So, this is fine. Now, here, so you can see the whole derivation, I have already done it actually, and so finally it comes out to be like this 3r pi and all that. So, this looks very similar to the JKR mechanics that we get, but here everything, here we have got this convolution, this expression is there, and we also have in terms of this compliance, creep compliance. So, we like to see that if we say this is an elasticity problem, then whether we can get back the JKR or not. So, let us say that for linear elastic system. So, for linear elastic system C0, okay, so that will be equal to 1 upon E star, right, and that is independent with respect to time, and this Ki that will be equal to Ki square by 2 E star is equal to Wa, remember that Ki square by 2 E star. So, this is equal to Wa, that is the work of adhesion, okay, and then C's convolution F, so that can be replaced by F by E star, okay. So, these things can be done, and then you replace all that. So, you substitute that. So, this will be equal to 3r by 4, and here this is C0 into Ki. So, let us say 3 pi r by 2 and C0 into K. So, 1 by E star into Ki. So, Ki is equal to square root of 2 E star into Wa square, okay, plus C star is F by E star over here, plus this is C0 is 1 upon E star and Ki is square root of Wa 2 E star into square root of this is 3 pi r by 2 and C0 is 1 upon E star and Ki star is square root of 2 Wa into E star, okay. This is square, this term whole thing is square, plus this is 3 pi r and this is F by E star, like this. So, we have all these things. Now, if I now do the algebra, we will get something like this. Let us say E star into A cube by T to A cube of okay. So, this is equal to, this will be 3 r by 4, yeah, and this is 3 pi r by 2 and this is square root over here. So it is square root over here is already gone there. So it is square root of 2 E star into W A plus this is F plus this is E star is already gone. So it is square root of 2 W A E star, okay, into this is square root of here this square. So let us make it square here. So it will be 2 E star. So E star square. So it is 2 here. So it is it will be equal to 3 pi by r, and 2 gets cancelled. So it is W A, and this is E star plus this is 3 pi r into F by, further simplification has to be done. Okay. So I do not have much time, but we can do that. So finally, after doing all that, okay, we can actually show that we get back this particular expression. So the way that I was trying to solve this problem, the simplifying that I was trying to do, so you do all that, okay, exactly that I was doing, and I have done it over here, and you can see that finally we will get back this expression. So this is actually this JKR equation that we have. So what I mean to say is that what we have now over here, this relation, that is a more general form, okay, which is applicable for both viscoelastic and elastic system, but over here, okay, we can easily get this JKR relation. Now the question is that what do I do as far as this viscoelasticity is concerned? How do I find out that A, okay, at some time t? So that needs to be found out. So for that we need to have the expression for Ki. So Ki, so that is the mode 1 intensity factor that can be very easily related, okay, to this fracture energy or work of adhesion for elastic system. That is not correct for the same expression will not work, okay, for the viscoelastic contact. So for viscoelastic contact, therefore we need to have some kind of model equation needs to be used, and that is there, okay. These points have been discussed very nicely in these papers, okay, you can have a look at it. So in a sense that what one needs to do it is that C, okay, C is this compliance, how that varies with respect to time. Now one can actually relate from the data, experimental data, one can get this Ct, okay, as a function of C0 plus C1 into T to the power m, let us say, and then the stress intensity factor, okay. For an elastic system, this capital Z will be equal to 1, but viscoelastic system one is to find out what is the Z, and there is where the models and all these things comes, and this, so this picture looks something like this, quite an involved equation, but nevertheless the expressions are there, and one is to use numerical methods, okay, to do this. So Z can be related to what is known as this cohesive zone size, and this is over here in which there are cohesive deformations and all these things are going on. So that is actually basically size of the contact zone, this is called, this is capital L, and then there is an expression for Lm, there are expressions for Cm, omega m, gamma m, all these expressions are there. Remember here actually it has not come out properly, but this is a star over here, that means this is dA by dt. So this expression is dA by dt over here, okay. So this dA by dt can be found out. So over here I have written the more number. So here this dA by dt, this is dm by dt, oh, this dot did not come out properly, but that is all, that is the way it is. So in a sense that we have this relations of finding out this Z. So over here the Z can be found out by relating this expression, here this L by Lm, this is actually related to work of adhesion by this expression. So work of adhesion is there, sigma 0 is another term. So sigma 0 means it is the critical stress that is attained. Remember the Dugdale model I had talked about. So there was a critical stress sigma 0 at which the failure occurs. So it is very similar to that. So sigma 0 is the maximum stress that these two surfaces can hold, and one can use all these equations, and then one can find out, okay, then expression for this dA by dt, and by integrating this equation with respect to time one can get the A as a function of time. So that is all one has to do, and some problems have been solved. I mean I will like to do it in the next lecture, I would like to show you a little bit, not much, about how what does one go about it for solving this problem by using this formalism. So, I will stop here today. Thank you.